So in this video we're going to go over synthetic substitution and the remainder theorem. So what is synthetic substitution? Synthetic substitution is just an alternative to direct substitution. So let's write that down. It's just an alternative to direct substitution. Now, direct substitution is when you have to evaluate a function. So you are told this is the function f of x, and when you evaluate using direct substitution, you let x be 3 and you figure out what the output is. So you plug 3 in and you get the output. So what we're going to look at is something called synthetic substitution. So before we do, okay, I want to draw something for us. I'm going to draw a function, x squared plus x minus 6. And we're going to take a look at different parts about this function. Okay, this function, if I were to factor it, write it in factor form, here's my quadratic x squared plus x minus 6. If I was to factor this, this would become x plus 3 times x minus 2. Okay, so I'm going to graph it, but some things I want to get at are x plus 3 and x minus 2. If you were able to factor this to be x plus 3 times x minus 2, that means that these are the factors of this expression. So what does that mean to be a factor? Well, think about it. 7 is a factor of 21. What does that mean? That means 7 divides evenly into 21. And when we say divides in evenly, what we mean is there would be no remainder. Okay, the remainder would be 0. That gets at something called the Factor Theorem. Okay, so what we know, this is the x-axis. I'm just going to plot a few points. We know that x is 2 is an x-intercept and x is negative 3. If I plug in negative 3, I know I'm going to output, right, 0. Okay, so our x-intercepts are negative 3 and 2. And, okay, my vertex is going to happen at negative 1/2. It's going to happen somewhere down here. I'm just making a rough sketch of this. I just want you to see something. Okay, so just understand the values. When x is negative 3, you have an output of 0. When x is 2, you have an output of 0, okay? And your graph, you're just visualizing all of your inputs with their corresponding outputs here. Okay, so number 1, okay, what is the remainder of x squared plus x minus 6 divided by x plus 3? Okay, now we'll call that 1a. Now, you know what the answer is already because we just talked about it, but let's say we didn't. We would use synthetic division, right? We can use synthetic division because the divisor is linear, okay? And look, the coefficient on x is already 1. Everything's in standard form and I don't need any placeholders, so the number in the box would be negative 3. Then you'd have 1, 1, negative 6. Okay, bring down the first. We put that little thing here. Remember, this is where the remainder sits. 1 times negative 3 is negative 3. 1 plus negative 3 is negative 2. Negative 2 times negative 3 is 6. Add that up, 0. Now I just asked what is the remainder. Okay, I didn't ask what anything else was. So the remainder is 0. And notice, what are you left with? The other factor of x minus 2 there. Now in part B, okay, I'm going to ask you to evaluate f of negative 3. So this says take the function f of x and plug in negative 3. So we're letting x be negative 3. Okay, now let's think about it. We already know what this should be if you look at the graph. Okay, x plus 3 is the factor, and it made x have an output of 0. Okay, the x value of negative 3 has an output of 0. So if I plug in negative 3, I get negative 3 squared plus negative 3 minus 6. That's 9 minus 3 minus 6, that's 0. All right, look, that remainder and that output are the same. Okay, So let's do another one. Number 2. What is the remainder of x squared plus x minus 6 divided by x minus 1? Okay, so first off, if we get in the mindset of this whole factor thing over here, okay, is x minus 1 a factor of x squared plus x minus 6? No. So is the remainder going to be 0? No. Graphically, okay, if x minus 1 is not a factor, that means that x equals 1 is not an x-intercept, which means we know that x equals 1 will have an output that is not 0. Okay, notice it's somewhere close to being negative 6. So let's see what the remainder is. Okay, so we put 1 in the box. We don't need any placeholders. 1, 1, negative 6. Okay. Bring down the first. 1 times 1 is 1. 1 plus 1 is 2. 2 times 1 is 2. Add the column. That gives us negative 4. So the remainder is negative 4. And in that, let's call that part A, and in part B, I want you to evaluate f of 1. So I want you to plug 1 into f. And what would we get? We would get 1 squared plus 1 minus 6. We would get 1 plus 1 minus 6. We would get negative 4. We get the same thing. Okay? Why is that happening? Well, if my remainder was 0, I would have an x-intercept, right? My remainder is negative 4. That means I am 4 off from being 0. 4 below 0 would be an output of negative 4. Is this always going to happen? Yes, this is always going to happen. This is called your remainder theorem. Okay, so what your remainder theorem says, this is in polynomials, okay, your remainder theorem says, let's say you have 2 polynomials. You have f of x and you have the polynomial x minus a, okay? So what it says is the remainder of f of x divided by x minus a is equal to f of a. Okay, so what that would mean is if I took x squared plus x minus 6 and I divided it by x minus 2, okay? The remainder of this would be equal to if I just plugged 2 in. Okay? So notice, the remainder of x squared plus x minus 6 divided by x minus 1 was negative 4. And if I just plugged 1 directly into my function, okay, I would get negative 4. These two will always be the same because, if you think about it, if this is a factor, x minus 1, okay, then that means that when x is 1, you would output 0. But since it's not a factor, you're not going to get 0 here, and this would end up being how far you are from 0, okay? So this is called the remainder theorem, and then the remainder theorem is what you can use to now do what's called synthetic substitution. Sometimes it's shorter than direct substitution, sometimes it actually ends up being longer than direct substitution. So we're going to evaluate, okay, we're going to evaluate f of negative 2 using synthetic substitution. For f of x equals negative x to the third plus 5x minus 2. Okay, so first off, let's see how we're going to use synthetic substitution. So saying we want to evaluate when x is negative 2, okay, would be the same as saying, okay, if we divided f of x by x plus 2, what would our remainder be? Because if x plus 2 is a factor of this expression, okay, then that means that when x is -2, I would have an output of 0. So whatever the remainder is here, that's what's going to be when I evaluate at -2. I would get the same output. So you put -2 in the box. Now you have to make sure. I need a placeholder here. This is -x⁻³ plus 0x² plus 5x minus 2. This is going to be -1, 0, 5, -2. Okay? And so remember, evaluating using synthetic substitution, all you're looking for is what's the remainder. So bring down -1. -1 times -2 is 2. 0 plus 2 is 2. 2 times -2 is -4. 5 plus -4 is 1. 1 times -2 is -2. Add that up, you get -4. So f of -2 is -4. Now, you might be saying, that's a lot of work. I could have just taken -2 and directly put that value in. And you would be correct, but, okay, this would give us -8 minus 10 minus 2. That would give us 8 minus 10 minus 2. That would give us -2 minus 2. That would give us -4. Notice you get the same thing. But understanding why synthetic substitution is a form of, why synthetic substitution is a form of evaluating, okay, is important. It's this idea that goes back to that factor idea of x plus 2 gives you the output. If it's not a factor, then this is how far you're off on a graph. This would be the output when this was the input. Okay, so that's it for synthetic substitution and remainder theorem.